Right now, wherever you are, you're probably sitting still or lying down. Maybe you've found a comfortable position and everything around you feels quiet and motionless. But here's something worth noticing, without any rush to understand it. You're not still at all. You're moving faster than a passenger jet, faster than sound. You're spinning with the earth beneath you, turning through space at over 1,000 miles per hour. And you can't feel any of it. There's no wind in your face, no sensation of motion, just stillness. We spend our whole lives in this kind of stillness that isn't really still. And most of the time, we never think about it. We don't need to. The world feels solid and unmoving, and that's enough. But tonight, we're going to look at something quietly unusual. Something that's been true since before there were people to notice it. Everything in the universe is spinning. Not everything at once, and not in the same direction. But almost nothing out there is truly, perfectly still. Planets turn, stars rotate, galaxies wheel slowly through the dark. Even the smallest things we know about carry some kind of spin with them. And this spin, this constant patient turning, isn't just a detail. It's not just something interesting that happens to be true. It's what keeps everything from falling apart. Without spin, planets wouldn't exist the way they do. Stars would collapse differently. The moon wouldn't hang in the sky above us. We wouldn't be here at all, in this form, in this moment. Spin is older than mountains, older than the Earth itself. It's been part of the universe since clouds of gas first started pulling themselves together in the dark billions of years ago. And somehow all that ancient motion still carries forward. It doesn't stop, it doesn't fade away easily. You're part of it right now, we all are. So tonight, let's take our time. There's nothing to solve here, nothing to memorize or hold on to unless you want to. We're just going to move slowly through this idea together. This strange, gentle fact that spinning is what holds the universe in shape. We'll explore why things spin in the first place, what happens when they don't, and what it means that we're standing here, turning quietly with everything else held in place by motion we can't even feel. You can stay as long as you like. There's no hurry. Let's begin by noticing what stillness actually feels like, and why we trust it, even when it isn't real. There's something deeply comforting about feeling still. When you're lying down at night or sitting somewhere quiet, your body tells you that you're not moving. The floor beneath you feels solid. The walls around you seem fixed in place. Everything has weight and position and permanence. This feeling is so convincing that we build our entire understanding of the world around it. We say things are sitting still or holding steady. We use stillness as our reference point for everything else. And in a way, we're right to trust it. Because even though you're spinning with the Earth, even though you're moving through space at speeds that would seem impossible if you could somehow step outside and watch, you're moving at exactly the same speed as everything around you. The ground is moving with you, the air is moving with you, the trees outside, the buildings, the clouds, the oceans, all of it turning together at the same rate in the same direction. So relative to your surroundings, you really are still. This is why we don't feel it. Why there's no wind from our motion through space. Why water sits calmly in a glass. Why we can walk in any direction without feeling like we're pushing against some invisible current. We're all moving together. It's a bit like being on a train that's gliding smoothly down the tracks. If you close your eyes and the ride is smooth enough, you can't tell you're moving at all. You could set a cup of water on the table in front of you, and it wouldn't spill. You could toss a ball straight up and it would come straight back down to your hand. Not because the train isn't moving, but because you and the cup and the ball are all moving together. The Earth is like that train, only much, much larger. and instead of tracks, it's turning through empty space held in place by nothing but its own motion and the gentle pull of the sun. We've been passengers on this train our whole lives. Every person who's ever lived has been a passenger, and none of us bought a ticket. We were born into the motion, and we'll leave it the same way. But here's what's interesting, in a quiet sort of way. Even though we can't feel the earth spinning beneath us, we can see the effects of it everywhere. The sun rises in the east and sets in the west, not because the sun is moving around us, but because we're turning. Day becomes night, becomes day again, over and over, because we're rotating toward the sun and then away from it. The stars wheel slowly across the sky over the course of hours. If you've ever watched the night sky long enough, you've seen them move. Not because they're circling us, but because we're turning beneath them. Even the way water drains from a sink, the tiny spiral it makes carries a whisper of the Earth's rotation, though it's so slight that other forces usually matter more. We live inside the spin. We've adapted to it so completely that it feels like nothing at all. But it's there, constant, patient, turning us through space at a speed we could never survive if we had to accelerate to it suddenly. And this same spin, this motion we can't feel but can't escape, is what's keeping us here. It's holding us to the surface, it's shaping the world around us, it's part of why the Earth is round, why the atmosphere doesn't drift away, why everything falls down instead of floating off. Let's look at that next, at what spin actually does, and why it matters so much. If you could step far enough back, far enough to see the whole solar system at once, you'd notice something. Everything is turning, not chaotically, not in random directions, but turning nonetheless. Each thing at its own pace, in its own rhythm. The Earth spins once every 24 hours. Mars takes just a little longer, about 24.5 hours. Venus turns so slowly that a day there lasts longer than a year. Jupiter, enormous as it is, spins faster than any of them. Once every 10 hours, its clouds racing across its face in great sweeping bands. The Sun itself rotates, though not all at once. Its equator spins faster than its poles, taking about 25 days to complete a turn, while the poles take more than 30. It's not solid, so different parts move at different speeds. Even the Moon is spinning, though it does so at exactly the same rate it orbits the Earth, which is why we always see the same face looking back at us. It's locked in step, turning and circling in perfect time. If you pulled back further, far beyond the solar system, out into the wider galaxy, you'd see that the Sun itself is moving. Not just drifting through space, but orbiting, circling the centre of the Milky Way along with hundreds of billions of other stars, all of them turning together in a slow, vast spiral. The galaxy itself is spinning, rotating once every few 100 million years, its arms trailing out like water swirling down a drain, only much, much slower. And if you could see even further, out to the edges of what we can observe, you'd find that other galaxies are spinning too. Some slowly, some faster, some in flat disks, some in elliptical clouds, but almost all of them carrying some kind of rotation with them. Spin is everywhere. It's not the exception, it's the rule. And this raises a gentle, patient question. Why? Why does everything spin? Why isn't the universe full of things that are perfectly still, just hanging in space, motionless? The answer quietly is that stillness is actually much harder to achieve than motion. When the universe was younger, when stars and planets hadn't formed yet, there was just gas. Vast clouds of hydrogen and helium spread thin across the dark, cooling slowly after the beginning of everything. And even then, those clouds weren't perfectly still. They had tiny motions, little currents, small drifts caused by gravity pulling unevenly, or by the shock waves from distant explosions, or just by the random motion of particles bumping into each other. These motions didn't cancel out, they didn't smooth away into nothing. Instead, as the clouds began to collapse under their own gravity, as they pulled themselves together over millions of years, those tiny motions got amplified. It's a bit like a figure skater pulling their arms in during a spin. As they bring their arms closer to their body, they spin faster. Not because they're adding energy, but because the spin they already had gets concentrated. The same thing happens in space. As a cloud collapses, any rotation it had, even just a little, gets faster and faster. The material spirals inward, spinning as it falls, and that spin never goes away. It carries forward into whatever forms from that cloud. A star, a solar system, a planet. All of them inherit the spin that was already there, written into the motion of the gas billions of years ago. So when we feel the Earth turning beneath us, even though we can't feel it at all, we're feeling an echo of something very old, a motion that's been carried forward patiently for longer than we can easily imagine. And that motion is doing something important. It's holding things up. Let's imagine something together, slowly and without any rush. Imagine a world that doesn't spin. Not the Earth. Let's not disturb where we are right now, but some other planet somewhere far away that formed without any rotation at all. Perfectly still, just hanging in space, held in orbit around its star but not turning. What would happen there? At first, it might not seem like much would change. The planet would still have gravity. It would still pull things toward its center, the way all massive objects do. A rock dropped from a height would still fall, but here's what would be different. There would be no day and night, not in the way we know them. One side of the planet would face its star forever, baking under constant light. The other side would face away into endless darkness, freezing in perpetual night. No sunrise, no sunset, just two halves of a world, divided permanently between heat and cold. The air, if there was any, would behave strangely. It would heat on the day side and rise, then flow toward the night side, where it would cool and sink. Enormous winds would blow constantly from one hemisphere to the other, trying to balance the temperature, but never quite succeeding. And everything on that world would feel the full, uninterrupted pull of gravity. Because here's the thing about spin that we don't usually notice. When something rotates, it creates a kind of outward pull. Not a real force exactly, but an effect. A tendency for things to want to move away from the center as they turn. You've felt this before, even if you didn't name it. When you're on a playground roundabout and it spins quickly, you feel yourself pushed outward. You have to hold on to stay in place. The faster it spins, the stronger that feeling becomes. The Earth does this too, just very gently, so because we're spinning, there's a tiny outward effect at the equator, slight reduction in how much we weigh compared to if the Earth weren't spinning at all. It's not much, you wouldn't notice it on a scale, but it's there. On our imaginary planet with no spin, that wouldn't exist. Everything would weigh slightly more. The full force of gravity, with nothing to counter it even a little. The atmosphere would press down harder. Mountains would be harder to climb. Not because they'd be taller, but because every step would carry the full weight of gravity without any relief. And over long enough time, millions and millions of years, the planet itself might even behave differently. Without the outward effect of spin, there'd be nothing to slightly push against the inward pull of its own gravity. The planet would be pulled into the most compact shape possible, a perfect sphere with no equatorial bulge at all. The Earth, because it spins, is actually slightly flattened at the poles and wider at the equator. Just by a little, about 27 miles difference in diameter. You'd never notice it by looking, but it's there. carved into the planet's shape by billions of years of rotation. A non-spinning world wouldn't have that. It would be perfectly round, pulled into symmetry by gravity alone. Now, this imaginary planet probably couldn't exist, not really. Nearly everything that forms in space inherits some spin from the cloud it came from. Stillness is rare, almost impossible in fact. But thinking about it helps us see something important. Spin isn't just motion. It's not just something interesting that happens, it's a kind of scaffolding, a structure. It holds things in certain shapes, creates patterns, pushes back gently against the collapsing pull of gravity. Without it, everything will be different. And with it, the universe becomes the way we see it, full of turning things, held apart by their own motion. Let's look more closely at how that works. There's something almost paradoxical about spin when you sit with it quietly for a moment. The same motion that holds things together is also what keeps them from collapsing completely. Think about the Earth again, turning steadily beneath us. All of its mass, the rock, the metal core, the oceans, the air, is being pulled inward by gravity. Every particle wants to move toward the center. That's what gravity does. It pulls things together. And yet the Earth doesn't collapse into a smaller, denser ball. It maintains its shape. It stays spread out, roughly spherical, with its surface far from its core. Part of that is because rock and metal are solid. They resist being compressed. They push back against gravity simply by being the materials they are. But part of it, a quiet, persistent part, is the spin. When something rotates, every piece of it wants to move in a straight line. That's just how motion works. Objects in motion tend to keep moving in the direction they were already going. But when you're spinning, you can't move in a straight line. You're constantly being pulled toward the center, forced into a circular path by whatever is holding you. Gravity or a rope or the structure of the planet itself. And that creates tension. It's the same tension you feel when you swing a weight on a string in a circle above your head. The string has to pull inwards to keep the weight moving in a curve, and the weight pulls outward and against the string, trying to fly away in a straight line. Neither force wins, they balance each other. On Earth, every part of the surface is doing this. Every mountain, every ocean, every handful of soil. All of it is being pulled inward by gravity, but also carrying an outward tendency because of the spin. At the equator, where the spin is fastest, this outward effect is strongest. Not strong enough to overcome gravity, not even close, but enough to make a small difference. If you could weigh yourself at the equator and then weigh yourself at the North Pole, you'd find you weigh slightly less at the equator. Not because gravity is weaker there, but because the spin is gently lifting you, just a little, against the pull downward. It's this balance, this quiet negotiation between inward pull and outward motion that shapes so much of what we see. The Earth bulges slightly at the equator because the spin pushes material outward there. The atmosphere is thicker at the equator for the same reason. Even the oceans are slightly deeper there, pulled into a shape that matches the spin. And this isn't unique to Earth. Jupiter spins so quickly, once every 10 hours, that it's noticeably flattened. If you could see it from above, you'd see that it's wider across the equator than from pole to pole. The difference is obvious, even in photographs. The planet is being stretched by its own rotation. Saturn is even more extreme. It spins just a little slower than Jupiter, but it's less dense, made mostly of gas, and so it flattens even more. You can see it clearly, an oval shape where a sphere would be if it weren't turning. Neutron stars, the collapsed cores of dead stars, impossibly dense, spin hundreds of times per second, and even they, despite their incredible gravity, show this effect. They bulge at the equator, They flatten at the poles. The spin shapes them, even when they're barely larger than a city. Spin doesn't erase gravity. It doesn't overcome it, but it resists it. Gently, persistently, it keeps things from falling all the way inward. It creates space between the center and the edge. It allows structures to form that wouldn't exist if everything simply collapsed under its own weight. And in doing so, it makes the universe we know possible. Let's see how that shape-making works, how spin doesn't just resist collapse, but actively creates form. If you have ever looked at pictures of planets, Earth, Mars, Jupiter, any of them, you've probably noticed something so obvious it barely seems worth mentioning. They're round. Not perfectly round, as we have talked about. Many of them bulge slightly at the equator because of their spin, but still, fundamentally, they're spheres. And if you think about it for a moment, that's a little strange. Rocks aren't naturally round. Mountains aren't round. If you break a stone in half, the pieces are jagged and irregular. Nature seems to prefer sharp edges, rough surfaces, random shapes. So why are planets different? The answer is gravity mostly, but spin plays its part too, quietly shaping the final form. When a planet is forming, when it's still just a cloud of dust and gas slowly pulling itself together, gravity pulls everything toward the center. Every particle, every grain of dust, every molecule of gas is drawn inward, attracted to every other piece. Over time, over millions of years, this creates a problem. If material from one direction falls in faster than material from another direction, the growing planet becomes lopsided, uneven, heavier on one side, but gravity doesn't like that. The heavier side has more mass, which means it has stronger gravity, which means it pulls even harder on everything around it, including the rest of the planet itself. So material shifts, flows, moves from the lighter areas toward the heavier areas, trying to even things out. And the only shape where everything is perfectly balanced, where every point on the surface is the same distance from the center, where gravity pulls equally in all directions, is a sphere. That's why gravity makes things round. But here's where spin comes in. As the planet forms, it's rotating. We know this because nearly everything in space inherits some spin from the cloud it came from. And as the planet pulls itself together, that spin gets faster, concentrated, amplified. The material isn't just falling inward, it's falling inwards while moving sideways at the same time. And this creates something important. It means the planet doesn't collapse into the densest possible ball. The spin prevents that. It holds material out, especially at the equator, creating that slight bulge we talked about earlier. So the final shape isn't quite a perfect sphere. It's an oblate spheroid, a sphere that's been gently squeezed at the poles and widened at the middle. The faster something spins, the more pronounced this flattening becomes. Earth's bulge is subtle, you'd never notice it by eye. But it's there, measured and confirmed, a permanent record of our rotation carved into the planet's shape. Saturn, spinning rapidly and made of lighter materials, is noticeably flattened. You can see it in photographs, the poles visibly closer to the center than the equator. And if something spun fast enough, if the spin were strong enough to overcome gravity's inward pull completely, the planet wouldn't stay together at all. It would fly apart, material flung outward into space. But that almost never happens. Gravity and spin find a balance, they negotiate. And the result is the shape we see. Round mostly, but shaped by motion. This process is patient. It doesn't happen overnight. When Earth was young, it was probably more irregular, lumpy, uneven, scarred by impact, still cooling and settling. But over time, hundreds of millions of years, gravity smoothed it. The rock flowed very slowly, like a liquid over geological time. Mountains that were too high sank, slightly under their own weight. valleys filled in, everything settled into the most stable configuration. And through it all, the planet kept spinning. The spin didn't stop the smoothing, but it guided it. It made sure that the final shape wasn't just round, but round in a particular way, wider at the equator, flatter at the poles, a shape written by motion and time. And this same process, this patient negotiation between gravity and spin, creates other shapes too, flatter shapes, shapes that spread outward instead of pulling inward. Let's look at those next. There's a shape that appears over and over in the universe. Not a sphere, something flatter, a disk. You've seen it around Saturn, those beautiful, impossibly thin rings circling the planet like a halo. Bands of ice and rock spread out in a flat plane orbiting together. But disks appear in other places too. Galaxies often take this shape. The Milky Way is a disk, seen edge-on from where we are. A flat spiral of stars, hundreds of billions of them, all orbiting the centre together in roughly the same plane. When new stars form, they're often surrounded by disks of dust and gas. Planets form from these disks. Our solar system came from one, billions of years ago. Even in your kitchen, if you've ever spun pizza dough or watched a potter shape clay on a wheel, you've seen the same thing happen. Spin flattens things. It spreads them outward into a plane, and the reason is quiet and consistent. When something spins, it has an axis, an imaginary line running through its centre that it rotates around. For Earth, that's the line connecting the North Pole to the South Pole. Material that was close to this axis doesn't move very fast. It's near the centre of rotation, so even though it's turning, it doesn't have far to travel with each spin. But material far from the axis, out at the equator for instance, has to move much faster to complete the same rotation in the same amount of time. It's covering more distance with each turn, and this creates a natural spreading. Material near the equator wants to move outward because of the spin. It's pulled by that same outward tendency we talked about before, the effect that makes you lean outward on a spinning roundabout. But there's nothing pushing it outward at the poles. There's no spin effect there, just gravity pulling straight down toward the centre. So over time, things migrate. Material drifts toward the equator. It settles into the plane where the spin is fastest, where the outward effect is strongest, and this forms a disk. Saturn's rings are an extreme example. They're made of countless pieces of ice and rock, each one orbiting Saturn independently, but all of them held in roughly the same flat plane by the planet's gravity and their own motion. If you could watch the rings over millions of years, you'd see collisions. Pieces bump into each other constantly. When they collide, they exchange energy and momentum. Pieces moving too far above or below the plane get nudged back down. Pieces moving too slowly fall inward. Pieces moving too quickly drift outward. But over time, everything averages out. The chaos smooths into order. And what remains is a thin, flat disk. All the particles orbiting together in sync like a river of ice flowing around the planet. Galaxies form the same way, just on an unimaginably larger scale. When the Milky Way was forming, it was a cloud of gas slowly collapsing under its own gravity and spinning. As it collapsed, that spin got faster, and as particles of gas orbited the centre, they collided with each other, gently over and over, and those collisions evened things out. Gas that was orbiting above the main plane would collide with gas below it. The collisions would cancel out their vertical motion, leaving them moving in roughly the same flat plane as everything else. Over hundreds of millions of years, the cloud flattened. It spread out into a disk. Stars formed within that disk, inheriting its shape. And now, billions of years later, We're part of that disk. Our solar system orbits within it. We're embedded in the plane, turning with all the other stars. Spin that creates order from chaos. It takes random motion and, through collisions, time smooths it into something predictable. Something flat, a shape that appears wherever things spin together for long enough. But spin can do more than just flatten. It can also push things to their limits. Let's look at what happens when something spins almost too fast to hold together. There are stars in the universe that spin so quickly they're barely holding themselves together. Not the Sun. Our star rotates once every 25 days or so, steady, patient, nothing extreme. But some stars spin hundreds of times per second. They are called pulsars, though that name describes what we see rather than what they are. What they actually are is neutron stars, the collapsed cores left behind after massive stars explode. When a star collapses, the same thing happens that we've talked about before. The spin it already had gets concentrated, faster and faster as it shrinks. A star that was rotating once every few weeks might, after collapse, rotate once every second, or 10 times per second, or 600 times per second. The fastest pulsar we know spins 716 times every second. Imagine that for a moment, without any rush. An object about the size of a city, made of matter so dense that a teaspoon of it would weigh as much as a mountain, rotating more than 700 times in the time it takes you to say the word second. At that speed, the surface is moving at a significant fraction of the speed of light. And the outward effect from the spin, that same tendency that makes planets bulge at the equator, is almost strong enough to tear the star apart. Almost, but not quite. Gravity holds it together barely. The neutron star is so dense, its gravity so powerful, that even spinning at these extreme speeds, it doesn't fly apart. But it's close to the edge. If it spun just a little faster, it would break. Material at the equator would be flung off into space, unable to hold on any longer. There's a limit to how fast anything can spin before the spin wins over gravity. And pulsars live near that limit. We see them as pulses of light, beams of radiation that sweep across space like a lighthouse as the star rotates. Each pulse is one rotation, a cosmic heartbeat, steady and fast. They remind us that spin has limits, that even motion has boundaries it can't cross without breaking something. But most things never spin that fast. Most things slow down eventually. Let's look at what happens when spin finally stops. Nothing spins forever. Over time, long, patient stretches of time, rotation slows. The Earth's spin is slowing right now, very gradually. So gradually you'd never notice it in a lifetime, or even in 1,000 lifetimes. But it's happening. The moon's gravity pulls on the oceans, creating tides. Those tides slosh back and forth, and that sloshing creates friction. Friction bleeds away energy, and as energy is lost, the spin slows down. Billions of years ago, a day on Earth was shorter, maybe 20 hours, maybe less. Billions of years from now, if nothing else changes, a day will be longer, 25 hours, 30. The Earth and Moon will eventually lock together, the way the Moon is already locked to us, showing us the same face always. But slowing takes time, immense amounts of time. For most objects in space, spin is patient. It doesn't give up easily. But when spin finally does stop, or when something collapses so completely that spin can't hold it apart anymore, gravity wins. Without the outward effect of rotation, without that gentle resistance, everything falls inward. This is what happens at the end of the largest stars, when they've burned through all their fuel, when there's nothing left to push back against gravity's pull. they collapse, and they collapse fast. The core falls inward in less than a second, compressing to extraordinary density. If there's enough mass, if the gravity is strong enough, not even the pressure of neutrons can stop it. The collapse continues past the neutron star stage, past any known structure of matter. And what forms is a black hole, a place where gravity has won completely, where nothing, not light, not matter, not anything, can escape once it crosses a certain boundary. The spin doesn't disappear though, even black holes rotate. They carry the angular momentum of the star that made them, concentrated now into something much smaller. But inside, past the point where we can see or measure, the spin may not matter anymore. Gravity has pulled everything to a place where our usual understanding stops working. It's the quietest ending, the most complete collapse. When spin can no longer hold things apart, this is where it leads. But before we get there, most things find a balance. Let's return to gentle emotions, to the kind of spin that keeps things circling instead of falling. The moon is falling. Right now, as you read this, the moon is falling toward Earth. It's been falling for over 4 billion years, and it will keep falling for billions more, but it never gets any closer. This seems like a contradiction at first. How can something fall without ever landing? The answer is one of the most elegant ideas in all of physics, and it doesn't require any mathematics to understand, just a quiet shift in perspective. The moon isn't just falling down, it's also moving sideways, very fast, about 2,300 miles per hour relative to Earth. And that sideways motion is enough that by the time it falls a certain distance toward us, the curve of the Earth has fallen away beneath it by the same amount. So it keeps missing. It falls and falls, constantly pulled by the Earth's gravity, but the ground keeps curving away, staying just out of reach. That's what an orbit is. It's not floating, it's not hovering. It's falling continuously but moving sideways fast enough that you never hit the ground. Every satellite orbiting Earth is doing this. The International Space Station is falling right now, and the astronauts inside are falling with it. That's why they feel weightless, not because there's no gravity up there, but because they're in free fall and everything around them is falling at the same rate. If the moon were to suddenly stop moving sideways, if something froze it in place, it would simply fall straight down. In a few days it would crash into Earth, but it won't stop. Nothing is slowing it down. There's no air up there, no friction to drain its motion, so it keeps circling, kept aloft by its own sideways speed. This is spin transformed into something else, not rotation around an axis, but revolution around a point. Orbital motion instead of spin, but connected by the same principle, motion holds things up. The Earth orbits the Sun the same way, falling toward it constantly, but moving sideways at about 7,000 miles per hour, fast enough that we never get any closer. All the planets do this. All the moons, every object in orbit anywhere is locked in this same graceful balance, falling forever, but never landing. It's another way that spin, or motion, like spin, keeps things from collapsing. The solar system doesn't fall into the sun because everything is moving. The galaxy doesn't collapse into its center because all the stars are orbiting. Motion creates structure. It holds things in place by never letting them be still, and we're part of that motion, inherited from the cloud that made us. Let's come back to that. The spin you're part of right now, the Earth's rotation carrying you through space, is older than you, older than humanity, older than the Earth itself. It came from the cloud 4.5 billion years ago. There was no Earth, no sun, no planets, just a cloud of gas and dust drifting in space, part of the wreckage left behind by earlier stars that had lived and died. And that cloud was rotating, slowly, gently, just a little. Maybe it inherited that rotation from the motions of the galaxy itself. Maybe it was nudged by a shockwave from a nearby supernova. Maybe it was just the accumulated drift of particles moving through space, never quite cancelling each other out. Whatever the reason, the cloud was turning. And as it collapsed under its own gravity, as it pulled itself together over millions of years, that rotation got faster. The spin concentrated, the way we've talked about before. The centre became the sun, the material around it flattened into a disk. And within that disk, small clumps began to form, dust stuck together. Pebbles became boulders, boulders became mountains, mountains became worlds. Each of those worlds inherited the spin of the disk they formed from. That's why all the planets orbit the sun in roughly the same direction. That's why most of them spin the same way. They're all carrying forward the rotation that was written into the cloud before any of them existed. Earth's spin is an echo of that ancient motion. When you feel the sun on your face in the morning, you're feeling the result of a rotation that's been unbroken for billions of years. The same spin that shaped the solar system is the spin that gives us day and night. The same motion that flattened the disk is the motion that turns us toward the stars each evening. We didn't choose this, we inherited it. Every person who has ever lived has lived inside this motion. Every tree that has grown, every ocean wave, every breath of wind, all of it part of the same turning that began before there was anything solid to turn. It's humbling in a quiet way. We're passengers on something much older than we are, carried along by momentum we can't feel but can't escape. And that's not uncomfortable, it's just true. Let's rest with that thought for a moment. There's something reassuring about knowing that the spin holding us here has been so reliable. 4.5 billion years, every single day, every single rotation, the Earth has never stopped. It's never forgotten how to turn through ice ages and warm periods, through the rise and fall of continents, through the evolution of life from single cells to everything we see around us today. The planet kept spinning. It spins when we're asleep. It spins when we're not paying attention. It doesn't need us to maintain it or worry about it. It just continues. And that spin is part of what makes life possible. Without it, we'd have no day and night. One side of the planet would bake under endless sun, while the other froze in permanent darkness. The air would flow in strange, violent patterns. The oceans would behave differently. Weather as we know it wouldn't exist. But with it, with this steady, patient rotation, we have rhythms. Morning becomes afternoon, becomes evening, becomes night. The cycle repeats. Plants grow toward the light, animals sleep and wake. Tides rise and fall in response to the moon's pull, itself a dance of orbital motion. The spin creates patterns we can rely on, and it asks nothing of us in return. We don't have to keep the Earth turning. We don't have to monitor it or maintain it. It simply does what it's been doing since before there was anyone here to notice. There's a kind of comfort in that if you let yourself feel it. We live on a world that turns without our help, held to its surface by gravity, carried through space by motion we inherited from a cloud that existed before the sun. None of it needs our permission. None of it waits for our understanding. It just is, and we get to be part of it, quietly, without having to do anything except be here. The spin that keeps everything from collapsing, the motion that shapes planets and galaxies and solar systems, is the same spin that brings the sunrise to your window each morning. Reliable, ancient, patient, still turning after all this time. Let's think about just how long that time has been. 4.5 billion years. It's difficult to hold a number like that in your mind. It doesn't fit comfortably into the way we usually think about time. A human lifetime is, if we're fortunate, around 80 or 90 years. That feels long when you're living it. There's time for childhood, for growing up, for building a life, for watching seasons pass over and over. But compared to the age of the Earth's spin, a human lifetime is almost nothing. If the Earth's entire history were compressed into a single day, 24 hours, humans would appear in the last few seconds before midnight. All of recorded history, every civilization, every empire, every person who has written anything down would fit into the final fraction of a second. And through all of it, through every moment of that vast, patient stretch of time, the Earth has been turning, the same rotation, the same direction. Slowing down, yes, but so gradually that the change is invisible across thousands of human lifetimes. Dinosaurs lived and died while the Earth spun. They walked under the same sun, saw the same stars wheel overhead at night, felt the same rhythm of day and night that we feel now. Before them, for billions of years, there was no life on land at all, just oceans and microscopic organisms, and a planet turning beneath an empty sky. And even before that, before there was any life at all, the Earth was spinning, newly formed, still molten in places, constantly bombarded by asteroids but already rotating. The spin is older than almost everything we can point to. It's one of the few things that has remained constant while everything else changed. Continents have drifted, mountains have risen and eroded away. Oceans have formed and dried up. Species have appeared and gone, extinct. The atmosphere has changed composition multiple times, but the spin continued. It doesn't hurry, it doesn't slow down quickly, it just persists, patient and vast, carrying everything forward. And knowing that, knowing we're part of something so old and so steady, can make us feel very small, but also strangely held, because that same ancient motion is what keeps us here, safe, turning quietly through space, still spinning, still here. And so we come back to where we started. Right now, wherever you are, you're still turning, moving through space at over 1,000 miles per hour, held to the surface by gravity, carried along by a motion that began before there were oceans or continents or anything alive to notice it. You can't feel it. You never have. You never will. But it's there. The same spin that shapes galaxies and prevents collapse. The same motion that creates day and night, that causes the stars to wheel overhead, that keeps the moon in the sky. It's holding you here, gently and continuously, without asking for anything in return. There's nothing you need to do about this, nothing to solve or remember or hold on to. It's just a fact, a quiet, persistent fact. The universe is full of spinning things, and you're one of them. Not because you chose to be, but because motion is what keeps everything from falling inward. Because spin is written into the structure of how things form and how they last. And that spin, your spin, Earth's spin, the spin of everything around us, will continue long after this moment has passed. The Earth will keep turning, the sun will keep rotating, the galaxy will keep its slow, vast spiral. All of it patient, all of it reliable. You can rest with that if you'd like. There's no hurry to go anywhere, no need to understand it all completely. You're part of something very old and very steady, and it will keep turning whether you think about it or not. So you can stay here as long as you need to. Let the ideas settle, or let them drift away. Either is fine. We'll be here, turning quietly whenever you come back. If you'd like to stay with us for more gentle journeys through space and time, you're welcome to subscribe, but there's no pressure. We'll keep exploring either way. Thank you for spending this time with us tonight. Sleep well or stay curious, or simply rest. We're still here, still spinning, still held by motion we can't feel.